We do an equilibrium constant expression. Our generic expression is going to be that we have KEQ, so the equilibrium expression constant. You can use K or KEQ, and it's going to be the concentration of products over the concentration of reactants. And those will actually be raised to the power of their stoichiometric coefficient. So I'm going to put just a generic A up here and a generic B down here. It's important to know that there are no units for KEQ. So just so you don't forget, there are no units here. So let's go ahead and take a look at an example. So we have this hydrogen plus iodine that form hydrogen iodide. And so in this, we have our hydrogen iodide is going to be our products. And so that's going to go on the top. Let me grab this one. So our KEQ value is going to be equal to, on the top, hydrogen iodide. And that's going to be raised to the stoichiometric coefficient of 2. Okay, so it's going to be raised to the second power. And then on the bottom, we want to have the concentrations of our reactants. So it's going to be the concentration of hydrogen gas times the concentration of iodide gas. Or iodide should actually be a solid in that case, but that's okay. Could be a gas as well. So that would be what our expression would be for this one. And then once we have our expression written out, we can go ahead and take a look at how to calculate some values. So the first one that we're going to do is what is the KEQ when we have these concentrations. Okay, so we're going to go ahead and just plug these numbers in for each one of the variables that's in this equilibrium expression. So in this case, we're going to put the 7.2 on the top for our hydrogen iodide concentration. And then we have to remember that we need to square that number. And then on the bottom, we're going to have the 2.0 for hydrogen and then the 3.0 for iodine. Okay, so to do my math, you'll see my calculator here, so 7.2 squared, and then 3 times 2, of course, is 6, so I'm going to divide that by either 3 times 2, or you could just put 6 on the bottom, enter that, and I get 8.64. We started with 2 sig figs in each one of those, and so our final answer should be 8.6. That is our equilibrium constant then for this particular situation. And then the last thing that it asks is what is the concentration, the molarity of hydrogen iodide if we have a different equilibrium expression and then 2 other concentrations. And so we want to know in this particular case, we know that the equilibrium expression, or excuse me, the equilibrium constant is going to be 0.72. We want to know what HI concentration would be. We know that is squared. And we know that the other 2 on the bottom are going to be 1.3 times 1.6. So we're going to go ahead and plug all of these in. We're going to solve for HI. And you can make that, you can substitute in for that X if you really want to. So I can go ahead and do that. I can say, okay, we're just going to make this X squared on the top because that's my unknown. So that's something that you can do there. And so when we rearrange these, we're going to multiply all these. So X squared is going to be equal to 0.72 times 1.3 times 1.6 all together. And when I do those, so let's see, 0.72 times 1.3 times 1.6, we get 1.497. 6, and I'm just going to go ahead and keep all of those numbers so I don't have rounding errors in my intermediate. So 1.4976. Now to get x by itself, we're going to have to take the square root of that. So x is going to be equal to the square root of 1.4976, which when we take the square root of that, find my square root button, so second square root, second answer. It's the fastest way for me to get that in there. And so I end up with a value of, in this case, I'm going to round to sig fig, so 1.2 molar is the concentration.